So it is time now to consider the two most important theorems for us, that is to say the Fisher-Tippett theorem that tells us how the partial maxima, when properly rescaled, converge towards a generalized extreme value distribution, and the Pickands-Balkema-de Haan theorem that conversely tells us how the excesses, the rescaled excesses, will converge towards a generalized Pareto distribution. Moreover, we will see that the Pickands-Balkema-de Haan also tells something more if we consider the peaks over threshold approach. But let's start from the Fisher-Tippett.
The Fisher-Tippett theorem dates back to 1928, and despite being a fundamental theorem in statistics, I would say as important as the CLT, it is unfortunately ignored by many people trained in statistics, not to speak about people trained in other disciplines for whom statistics is just a tool. Okay, I think that this is both a pity and a shame because of the importance of the theorem. The theorem tells us that if we have a sequence x1, xn of IID random variables, we will see that if we drop the IID hypothesis, we need to introduce some corrections to the theorem, but it can be managed. So if this sequence of random variables are IID, then what happens? If there exist constants an, bn, such that an is positive and bn is real, and we can use these constants to normalize the partial maxima generated by the sequence of random variables, then if these normalized maxima converge towards a non-degenerate distribution G, then this distribution needs to be necessarily one of the three extreme value distributions that are the Fréchet, the Weibull, and the Gumbel. On your screen, you can see the three distributions, the Fréchet, the Weibull, and the Gumbel. As you can observe, two of them, the Fréchet and the Weibull, share a parameter alpha that we will call the tail parameter or the shape parameter. This parameter is rather important because it tells us how the tail of the distribution behaves. Conversely, the last distribution, the last extreme value distribution, the Gumbel, does not have the parameter alpha. Now, if you look just superficially, these distributions, they look quite similar, so they seem more or less the same distribution. In reality, we will see that each distribution corresponds to a specific behavior of the maxima. So the three distributions really characterize the behavior of the maxima and so also of the original random variable that generates the maxima. The generalized extreme value distribution is then nothing more than a way of representing the three extreme value distributions in one simple formula. So what we see is that actually the generalized extreme value distribution is a family of distributions. Depending on the value of the parameters, in particular the parameter xi, we will see that the GEV becomes a Fréchet, a Gumbel, or a Weibull. The connection between the xi parameter of the GEV and the alpha parameter that, for example, we have seen in the Fréchet is very simple. Xi is nothing more than 1 over alpha. Now, if xi is positive, we are in the so-called Fréchet case. If xi is negative, we are in the Weibull case. And if xi is 0, we are in the Gumbel case. So, just looking at the value of xi and obviously testing for the significance of that value, we will see we have a possibility of making distinctions among the different extreme value distributions just using one simple representation, that is the GEV. Now, before entering into more detail, I would like to give you the intuition behind the different cases, the Fréchet, the Weibull, and the Gumbel. Now, the Fréchet will be the situation of all those distributions that we will call fat-tailed. So, with the famous fat-tail behavior. These are distributions that for us can be particularly risky and that have an infinite upper bound. So you are in the Fréchet class only if the upper bound of the distribution generating the maximum is plus infinity. The Weibull class is a class that deals with a lot of distributions that can be more or less risky, so also quite risky, but that are all characterized by an important thing. That is to say, the upper bound is finite. So in the Weibull class, we find all those distributions that have a bounded support. So it is quite immediate to say that, for example, a distribution like the uniform or like the beta is in the Weibull class because it has an upper bound. In the Gumbel class, we find all those distributions that are typically thin-tailed. That is to say, distributions that decay quite quickly in the tail, that are not able, in most of the cases, to generate extremely risky phenomena. We speak about distributions like the normal or the exponential. There is a very important exception in the Gumbel class that is represented by the log normal. As we will see, the log normal is in the Gumbel class, so in principle is a distribution that should not be as risky as a distribution in the Fréchet class, but depending on the sigma parameter of the log normal can be a very wild animal, can be a very tricky object. And in fact, in data, sometimes it's very difficult to distinguish between a Pareto and a log normal. So the log normal is a fundamental exception in the Gumbel class. Apart from the log normal and all the distributions that can be considered transformations of the log normal, then all the other distributions in the Gumbel class are essentially distributions with thin tail and unbounded support. But the fact that it is unbounded is not particularly relevant because the tail closes down very quickly. Via transformations, it is also possible to connect the different types of tails, so the different types of limiting extreme value distribution. So it is always possible to move from a Fréchet to a Gumbel, from a Gumbel to a Weibull by inducing transformations in the data. And sometimes these can be useful in applications. I already told you that the exponential is in the so-called Gumbel case. To be more formal, we will say that the exponential is in the maximum domain of attraction of a Gumbel distribution. But before the formality, let's consider a simple example. So let's consider a sequence of standard exponentials, and as usual, we assume them to be independent. Now, we can find appropriate constants, an and bn, and for the moment I give you the constants. For an, we can take an equal to 1 for all n's, and for what constants bn, we can take the log of n. Okay, if we take these constants and we use these constants to normalize the partial maxima, then the distribution of the partial maximum can be shown to converge towards a Gumbel. Okay, let's now give the definition of maximum domain of attraction. So we say that a given random variable x or its distribution function f, it's exactly the same, belong to the maximum domain of attraction of one of the three extreme value distributions if the normalized partial maximum converges in distribution to one of the three extreme value distributions. So we say that an exponential, as we said in the example, belongs to the maximum domain of attraction of the Gumbel distribution because if we normalize properly the partial maxima generated by a sequence of independent exponentially distributed random variable, then these partial maxima properly rescaled will converge towards a Gumbel distribution. Since we will use it in what follows, on your screen you see the definition of generalized inverse. So I guess it's just a repetition, but repetita juvant, the Latins used to say. Now, in extreme value statistics, even if we will not enter into the details, because it's a complicated part of the theory, even if extremely useful and fascinating, but it takes a lot of time, so we don't have the time for doing that. But you can find all the details in the books I have already suggested you. Okay, even if we do not enter into much detail, you can imagine that there are conditions that we can check for a given random variable or its distribution function to immediately understand to which of the different extreme value distributions the normalized maxima will converge. We will say something about the conditions to be in the maximum domain of attraction of a Fréchet, because that is the most interesting case for us from a practical point of view, and I leave the conditions for the Gumbel case and the Weibull case to you. In reality, the conditions for the Weibull case are not particularly complicated. They are in line with those of the Fréchet case. Those of the Gumbel case, conversely, are a little bit more cumbersome. We have to check extra von Mises conditions and so on. So we skip that part. You find all the details in the textbooks if you are interested. If we focus our attention on the Fréchet class and we zoom in into the tail of a Fréchet distribution, what we can immediately notice is that this tail decays as a power law, so as x to the minus alpha, where alpha is the parameter of our Fréchet. So in terms of the xi parameter, that will be x to the minus 1 over xi. Now, this fact is a very important starting point for us, also to solve many of the ambiguities that we can find in the statistical discourse when we speak about fat tails. The question we want to answer is the following. If we consider a generic random variable and its distribution function f, how far the tail of the random variable can be from a power law decaying tail to be still in what we call the maximum domain of attraction of a Fréchet? So what are those distributions whose tail somehow decays as a power law and that are in the Fréchet class? Using some important results by Karamata, we can give the following theorem. The theorem tells us that a distribution function f is in the maximum domain of attraction of a Fréchet distribution of parameter alpha positive if and only if the tail of f, that is to say f bar, that we recall is the survival function 1 minus f, can be written as a regularly varying function. That is to say, it can be written as x to the minus alpha, the power law decay part, times L of x, where L of x is a slowly varying function. So the class of all the distributions that are in the maximum domain of attraction of a Fréchet is the class of those distributions whose tail is regularly varying. Those are the distributions that we will call properly fat tails. So a fat tail is not, generally speaking, synonym of heavy tail. We will see that heavy tail requires something else. A fat tail is a regularly varying tail. We will see that if a tail is fat, it is also heavy, but we can have heavy tails that are not fat. Now, Once this is the case, then we can find our constants Bn and An. For what concerns Bn, it is always equal to 0. For what concerns An, it can be expressed using the generalized inverse that we have seen a few minutes ago. So I repeat, a distribution is in the maximum domain of attraction of a Fréchet distribution of parameter alpha positive if and only if the tail of the distribution f is fat. So if we are considering a properly fat tail distribution, that is to say, the survival function of f bar, decays regularly. So it's a regularly varying function. That is to say, a function that we can express as the product of a power law component and a slowly varying function. What is the meaning of this? The meaning of this is that for x growing towards its right-hand point, the slowly varying component tends to vanish and only the power law tail remains. As we shall see, in the class of fat-tailed distributions, we naturally find the Pareto, also because the Pareto, in a sense, is a Fréchet distribution, but also all the other distributions like the Bohr distribution or the log gamma distribution that in the tail decay as a power law. All distributions in the Fréchet class are fat, so they are fat-tailed distributions, and we will see they are also sub-exponential, heavy, long, and so on. Later in this lesson, for example, we will consider the different types of tails, and we will see that saying that a distribution is fat tail is not a synonym of long tail, heavy tail, and so on. In statistical terms, if you want to be precise, and if you want to avoid confusion, which is a big problem when we deal with these kind of things, you have to distinguish between a fat, a long, a heavy, and so on tail. It is an extremely simple exercise for mathematicians like you to verify that the Pareto distribution is trivially in the maximum domain of attraction of a Fréchet distribution. In fact, if we consider the survival function of a Pareto distribution, f bar, this can be written as k times x to the minus alpha, where k is nothing more than a constant term. Now, given this, we can easily obtain an and bn. bn is always equal to 0, and an is easily obtained via the generalized inverse. Now, this is what I wanted to tell you for the moment with respect to the Fisher-Tippett theorem and the maximum domains of attraction. We will be back later with extra details when needed, for example, when we remove the IID hypothesis, which is at the basis of the theorem. Let's consider now the Pickands-Balkema-de Haan framework. Now, to do that, we have to introduce the concept of excess distribution, because you remember that what I already told you, the Pickands-Balkema-de Haan theorem is linked to the peaks over threshold approach, and in that approach we set a threshold and we look at all the observations above that we called excesses. Okay, so we need to say a little bit more about those excesses. Now, if we consider a random variable f with distribution function f, and we take a threshold u, what we can define is the so-called excess distribution that you can see on your screen. This is nothing more than the distribution related to what happens to x when we move above the threshold u. So it's the probability of our random variable x rescaled by the threshold u being smaller than equal to small x, given that our random variable x is actually above u. So we are considering what happens in the tail above u. Now, this excess distribution fu of x can be written as you see on your screen, and it is a very important ingredient of what we are gonna say in the Pickands-Balkema-de Haan theorem. Now, what I want to stress is that this excess distribution sometimes can be defined in a slightly different way. So instead of considering the probability of x minus u being smaller than or equal to small x, given that x is above u, we can remove the minus u part. Some authors call that the exceedance distribution to distinguish between the excess and the exceedance. At the end of the day, the results that we get are the same. There is only to take into consideration this rescaling by minus u that can be present or not, and necessarily that appears then in the limiting distribution as well. The Pickands-Balkema-de Haan theorem then tells the following. If we have that our distribution function f belongs to the maximum domain of attraction of one of the three extreme value distributions that we have considered, so the Fréchet, the variable, or the Gumbel, then I can always find a threshold u that, if large enough, that is to say for u growing towards the right-hand point of our random variable behind the distribution f. Okay, in that case, what I have is that the excess distribution I can define can be very well approximated by a generalized Pareto distribution. It means that if I consider the excesses above a very high threshold, then those excesses will follow a generalized Pareto distribution. This generalized Pareto distribution will have a parameter psi and a parameter sigma that we expressed as sigma of u, because it will depend necessarily on the threshold u. In reality, what we will see in application is that once we find the minimum threshold above which the generalized Pareto approximation works, then increasing the threshold does not change our results. For example, we will see that sigma of u necessarily changes because it's a function of u, but the psi parameter, so the tail parameter, remains the same. And this is, for example, one of the heuristics that we can use to check if our fitting is correct. So we will see that if we change the threshold of our fitting and psi is more or less the same, so remains more or less stable, then it means that probably we are close to the real threshold that makes the Pickands-Balkema-de Haan theorem work. Now, this theorem is very important for the fundamental and useful implications it has in practice. Now, the class of distributions that satisfy the requirements for the Pickands-Balkema-de Haan theorem is quite large. We can say with very good approximation that if we restrict our attention to the continuous distributions, unless we really think of pathological cases, we can safely say that they are all included. So for continuous distributions, we have these very strong results that tells us that when we consider the very, very upper tail of the distribution, then this tail can be approximated by a generalized Pareto distribution. And this is extremely powerful. For what concerns discrete random variables, it's a little bit more complicated. There is a little bit a longer discourse to be made, but we skip it here because it's not of interest for us. So let's consider what we can say if we take into consideration the two theorems we have just discussed. And I mean the Fisher-Tippett and the Pickands-Balkema-de Haan. So, if we consider the Pickands-Balkema-de Haan theorem, we have that a very large number of tails of distributions, in continuous case, can be safely approximated using the generalized Pareto distribution, and this is what we call the generalized Pareto distribution approximation, or the generalized Pareto approximation. And if we consider the peaks of the threshold method, as we shall see in applications later in the course, there we have that the excesses, that is to say, all the observations that lie above the threshold when we consider the distance from the observation itself to the threshold, then the excesses follow a generalized Pareto distribution. We should also see that we have more results. For example, we know that the number of exceedances, so if we count the number of times in an ID sample we have these exceedances over the threshold, then the number of those exceedances follow a Poisson process. We will see that most of the times it is a homogeneous Poisson process. If it is not homogeneous, it has some particular implications. But we know that in any case, the number of exceedances will follow a Poisson process. And even more, and this is a first link between the GPD and the GEV, if we consider the maximum of the excesses, so we are not only interested in modeling the excesses and looking at their distribution that will be in the limit at GPD, but we consider the maximum of the excesses, then the maximum of the excesses is GEV distributed. I would like to conclude this second part of our fourth lesson by stating what is actually the connection between the GEV, the Generalized Extreme Value Distribution, and the GPD. What we have said is that we have different approaches to play with the distributions. Typically with the GEV we use the block maxima, for the GPD we use the peaks of the threshold. You can also, if you want, combine the two approaches, as we shall see when you don't have IID observations, but in any case what we have is that, as I told you, it is not so important which of the two approaches you will use, because in the limit you will get the same result. What will change is obviously the way in which you look at the phenomenon, because in one case you consider the partial maxima, in the other one you consider the excesses. So in any case, for example, if you consider the excesses, you always have to consider that you are considering the observations above the threshold. So at a certain point you have to put back the threshold if you want the actual values. Okay, but these are minor things. The connection between the GEV and the GPD is very useful, and it tells us that we can always choose the method that is more convenient for our dataset to analyze the maxima, because at the end of the day we can reach very important and stable results. So the connection between the two important theorems, the Fisher-Tippett and the Pickands-Balkema-de Haan, is that the class of distributions F such that their normalized maxima converge towards a generalized extreme value distribution, one of the three types, this class of distributions constitute a class of distributions such that if we consider the excess distributions over a high threshold, then those excess distributions are well approximated by a generalized Pareto distribution. And even more, the Xi parameter that we get under the generalized extreme value distribution is exactly the same Xi parameter that we get under the generalized Pareto distribution. So this is very important because it tells us that we are free to choose the approach we want, but at the end of the day, the information about Xi, that is the most important parameter that governs the tails, is the same. And even the interpretation of the Xi parameter is the same. In the GEV case, we know that if Xi is positive, we are in the Fréchet class, which is the class where we find fat-tailed distributions like the Pareto. If we are considering Xi equal to 0, we are in the Gumbel class where we have thin-tailed distributions that somehow resembles in their tail behavior the exponential, and for what concerns conversely the Weibull class, we are considering the case Xi negative, and this is the class of all the distributions that essentially behave in the tail like a Weibull, and even more, they have a finite upper bound. Now, if we consider the GPD, so the generalized Pareto distribution, a positive Xi corresponds to the real Paretian case. So the generalized Pareto distribution behaves like a Pareto. So it has a power law decay as a Pareto. If we consider the case Xi equal to 0, the generalized Pareto distribution essentially is an exponential, which is in line with the Xi of the GEV. And if Xi is negative, the generalized Pareto distribution represents a short-tailed distribution, in line with the variable class.